So now that we've seen the pieces of the interpreter that we're going to build theoretically, let's take a look at the concrete implementation of our interpreter in Haskell. First, let's take a look at how we're going to build the parser. So the parser is actually going to be a Haskell function that transforms the program text into an abstract syntax tree. And to build that, we're going to use the Parsec parser library. So one key question is, what is that function going to output? And it's going to have to output an abstract syntax tree, but how are we going to represent that? And we can represent that by using an abstract data type that I'm defining here called calc_expr. And using the algebraic data type syntax in Haskell, we can define a calc_expr as being one of these alternatives. Either it's a number, in which case it has a value represented by an integer, or it's some arithmetic expression, compound expression, a negation, a sum, a difference, or whatever it is. So we just need to build a value of that data type. And to do that, we're going to use this Parsec library. Now, to use Parsec, first we have to import its package, which is text.parseccombinators.parsec, or text parser combinators.parsec. And a Parsec parser is built of a series of rules. Now, each rule is built in a way that looks like a function definition, because it is a function definition, because that's the sort of thing that we build in Haskell. And so here's an example rule. To recognize a digit, we either want to recognize the character 0, or, that's what this funny thing looks like, the character 1, or the character 2, or all of the rest of the characters all the way up to the character 9. And then once we have one digit defined, we can use that. The reason that Parsec is called a parser combinator is because you can combine these little parser functions by using other parser functions to make new parser functions. So given this digit parser that we've made, we can generate a parser for a sequence of digits or a number by calling the many1 function on the digit parser, and that produces a new parser that takes one or more digits. And so once we've done that, we can go ahead and use that in the Haskell interactive shell GHCI by typing in something like this. If we say let result equal parsed number, and then give it a name that it will return if there's an error, and then our input, which is in this case 1, 2, 3, 4, then once we run that, the result will be the parsed out number 1, 2, 3, 4. So let's take a look at the actual parser that I'm going to give you for the homework assignment. So here's the assignment directory. This is what you're going to download in order to do the first assignment for this week. And if we take a look at the parser code, it goes ahead and does this import text parser combinators parsec, and then it defines this data type calc_expr that I showed you, and then it has a bunch of these parser rules. So we're defining WS, which means white space, to be either the character space or the character tab. So then spaces is many, 0 or more, white space. Then we can define expressions for, or define parsers to parse numbers. So the Parsec library gives us some of these functions that we wanted already. It gives us digit. We don't have to define that ourselves. So we can say that a number consists of one or more digits followed by some spaces. And we're using do notation here because we want to do something in sequence. First we want to look for one or more digits, then we want to look for some spaces. And then the value that this parser is going to return is the value returned by the many1 digit parser, which is going to be the sequence of digits that it's matched. So we'll store that in this number variable, and then we will return number, which is the constructor from the data type that we defined up here, and that takes an int as a parameter. And because the thing that we're parsing is a sequence of characters, this one or more digits will get stored in the number variable as a series of characters, which are the digits that we matched. And so in order to get the value of that as an integer, we have to call the read function and explicitly tell it that we're expecting to get an int out of it, because this is one of those cases where Haskell can't determine the appropriate type automatically, because when you're reading some arbitrary string, who knows what type is in it. But in this case, we tell Haskell that the type that's in it is an int, and it can happily generate an int from that series of digits, and then use that to construct a calc expr, which is the number case. So then we handle parenthesized expressions, which are important. Those weren't in the operational semantics that I described, but they're an important part of arithmetic expressions, so we're going to handle them. A parenthesized expression is just an open paren, so this p here matches this expr parser here, so it's going to run the expr parser. Then close paren, and then the value is the expr that was in the parens. So to actually be able to handle arithmetic expressions, we're actually going to do this clever thing here that Parsec handles, which is we're going to call its build expression parser function, which takes this table of operators. And if you remember the lesson on parsers, you'll remember that in order to handle operators of different precedences, we had to have a special thing. We had to have expr, and then we had to have term in order to separately handle different precedence levels. And here, once we add unary negation, we end up having to have 3 precedence levels in order to generate the right results when we do our parse to get the abstract syntax tree that we want that handles precedence properly. So what build expression parser does, it handles all of that for us. We just have to pass it this table, which is a list of lists, and each list is the list of operators at each precedence level. And it goes ahead and builds us a parser that does the thing that we want. And so expr here is a bunch of parenthesized expressions as the leaves, and then these 5 operators as the interior nodes, and it will give us a tree with that property. And then we define a full expression as an expression that has been terminated by a new line. And then we need to handle error conditions. In this case, if we get an error, we'll just go ahead and crash, call this error function. And if we don't get an error, the non-erroneous value is the value of the thing. And then we have this parseCalc expression function, which is our parsing function that we wanted. So let's go ahead and take a look at that in action. Okay, so I went ahead and tried to parse the calculator expression 1 plus 2, and as you can see it gave us this error, expecting digit space tab operator plus minus or new line, which is sort of an awkward list of things for it to be expecting, but those are all the things that would have been legal after the 2 here. And the problem here is that we had said that a full expression has to be terminated by a new line, so I have to go ahead and add a new line in here to make that work. And once I add in that new line, it will do the right thing. This is the root node of the tree is sum, and then the leaves are the number 1 and the number 2. And we'll actually be fixing this new line thing in a future version of the parser, because it's annoying and doesn't quite do what we want. But for now, an explicit terminator for the expression is a reasonable thing to have. And if we give this a more complicated expression, we can see that it does the right thing. The 1 plus 2 in parens is in parens, it should be. That binds tightly. And then the product binds more tightly than the quotient because they're the same precedence level, but the multiplication comes first. So that gives us exactly the tree that we expected. So that's how the parser is going to work. And in the next video, I'll go ahead and show you how we'll evaluate these trees once we have them.